And next we will hear from Eric Berkenpas, now the Senior Director for Exploration Technology at the National Geographic Society. Mr. Berkenpas studied electrical engineering at South Dakota State and the University of Maine. He has led groups in the development and deployment of highly specialized technology for all of National Geographic's needs, which has included projects incorporating drones, 3D printing, and state-of-the-art imaging software. Join me to welcome Mr. Eric Berkenpas to the stage.
Thank you, Maya. Thank you, Maya, and I'd like to thank Blueprint and Duke for inviting me here to speak. So, let's see if I can get it going. So I work on a team called Exploration Technology at National Geographic. We provide technology support for our explorers, grantees, and initiatives, and we build things that will help them do what they need to do. So this is an 8-month time lapse of ice formation on the north coast of Greenland. We actually captured that by putting a camera and having it take a picture of the sea every 10 minutes, and then we left it there, went back and picked it up. And people are always confused why I'm an engineer, why am I working at National Geographic? But National Geographic actually has a fairly extensive innovation history. They've created all kinds of tools at National Geographic to solve the problems of their explorers. So an example is they created this navigation tool called the solar compass, which is a way to actually navigate in the polar regions before GPS. They pioneered some deep sea photography, and we continue to work at National Geographic to support our initiatives. We work in the basement at National Geographic. There's a shop called basically it's the Exploration Technology Lab, and we have a rapid prototyping shop. We build all kinds of basically small run prototype systems there. We have a full machine shop, and it's actually kind of weird having a big machine shop right next to the 4 blocks from the White House, but we have that. So we build all kinds of tools for our explorers and initiatives, and one group called Pristine Seas, they're basically surveying or trying to survey and protect the most pristine, most untouched places in the ocean, had a problem. They used scientific divers to do surveys of these areas. They would basically go in on a ship of opportunity, they would do a reef survey, and then they would use that data to make a case to protect that area. And so they could only actually survey to diver depth. So what they needed was a tool to actually survey the deeper places, stuff beyond 200 feet. So we created this system. We call it the Dropcam. It's basically very simple. It's a glass bubble with a camera, some lights, computer inside of it, and a battery. And you tie a weight to it, throw it over the side of a boat. It falls to the seafloor. It's usually baited. It films for a while. Once it's done filming, it releases the weight using a burn wire. It's a little wire that actually corrodes rapidly. It goes up to the surface, and then sends out a signal to the Argo satellite network. You recover it, download the footage, and you see what was on camera. And so the unique thing about this system is it can actually go to full ocean depth. So we've deployed it to almost 11,000 meters, and we can do it cheaply. We've done a survey of the Puerto Rico Trench from a 40-foot sailboat, and I don't recommend it. It wasn't pleasant at all. But the advantage of this is we've been able to deploy this all around the world, in almost every biogeographic part of the ocean. And this is the kind of footage you get from the Dropcam. So we collect this video data, then we have a network of taxonomists that look at the imagery, figure out what's there, and then Pristine Seas uses this data in part to make their scientific justification. And they actually talk to local fishermen. They want to get them on board. One of the cases they use is this thing called marine protected area spillover, where if you protect an area, fish that are the ecosystem is going to heal itself, fish are going to leave, and it's actually going to be more productive for the fishery. And so they've been able to protect 17 places to date, and have established 5.2 million square kilometers of new no-take marine reserves in the last, since they started in like 2008. And now that we've deployed this so many places, we're actually looking at some of this data globally on a global scale. So this is 7 of the ocean's biogeographic regions, and we're looking at biodiversity versus depth, trying to figure out a way maybe we can use this technology to actually monitor ocean health on a global scale. And so we thinking about the Dropcam, we thought this is a great idea. We can put optical sensors into the ocean. We can make all kinds of biological measurements. But most of the life in the ocean actually lives in the pelagic zone, the space between the bottom and the top. It lives in this ecosystem called the deep scattering layer. And so how do you actually capture that? You can't tie a weight to it. It'll go to the bottom. It'll go right through the deep scattering layer. So there's a few ways to do it. You can use an AUV. You can use an ROV. These are tethered and untethered robots. And you can use a man-submersible, but they're all very expensive. So we came up with a concept called the Driftcam. The idea is you basically send this robot down into the scattering layer, and you're in communication with it. So you can ask it how deep it is, and you can tell it to go to different depths. It has a buoyancy engine on it, basically changes its volume and maintains its mass by actuating a piston. This guy Archimedes figured it out a long time ago that you could change buoyancy that way. And then we use an echo sounder to figure out where the scattering layer is. And so if the drift cam's above the scattering layer, we tell it to go, dive into the scattering layer. And so it's a little bit of a pain to use. I think it's about almost 200 pounds. It's relatively small. And we just chuck it in the water. It's got like a 2 million ISO equivalent camera on it, so it's pretty dark in the pelagic region. And you can actually see under starlight with this camera. And we've piloted it in a few projects. So this is the Driftcam actually in a shallow water test dive. It was kind of fun diving with it. And we found we were actually able to track the scattering layer. The deep scattering layer in most places migrates to the surface at night and feeds. It's the largest migration in the world. It's called the Deal vertical migration. And then after it feeds, it goes back down. And so you can see the black lines, the position of the drift cam versus time, superimposed over the echogram from our echo sounder. That this red is actually where the animals probably are. We're getting a lot of echo return. And then in the line, you can see that it gets red there and it goes to yellow. That's actually the number of species observed on camera. So we like this idea. We think we can refine it. We can maybe make the drift cam smaller and deploy more of them at once. And then one more example of a system that we've been deploying is our camera trap technology. So we actually have a history of deploying camera traps for our photographers. You can buy, like scientists typically use cheaper, low cost Bushnell or Reconic systems, but our photographers and media groups like to use big expensive cameras, so we develop basically a box and some electronics and sensors so that they can capture basically species walking past these cameras and leave these camera traps out for months, and then go and collect their footage and get hopefully high quality imagery. So this is an example of a shot. This is Steve Winter, wildlife photographer, and he was looking at urban wildlife interactions, and that was actually a leopard in the heart of Mumbai. And so he was able to use these camera traps to tell the story about urban wildlife, and actually had an interesting story. He found out that the lights were actually causing urban wildlife interactions, because in a lot of the towns, the people would go out into the forest to use the restroom, and because they kept moving the lights out, thinking it would make it safer, the people had to go further into the jungle, and which actually made things worse. So what he found was all you had to do was get porta potties into these villages for the people. So Blueprint actually asked me to come up with some ideas for challenges for you guys. So these are kind of some of the challenges that have been posed to me in the past, and I thought I'd just pose them to you. So the first one is, how do we monitor an ecosystem in real time? So we need to measure things like biodiversity. We need to detect poaching. We need to monitor productivity of the ecosystem. How do we do that? How do we do it on scale, and how do we do it cheaply so that we can know like what's going on in these ecosystems, and also so that like a protected area manager can make proper decisions. Challenge 2. How do we make an animal tracker that is less than 1 gram? This is a question that keeps coming up. The one I have in the picture, I think this one is like 2.5 grams. This is the low-tech pinpoint. It's an Argos-based GPS tracker. And the reason to do this is monitoring animal migration is important to make scientific justification to establish protected areas and wildlife corridors. And with large tracking devices, there's only a certain number of species you can do it on. So making them smaller and smaller and smaller means that you can get more data on small animals. And then challenge 3, how do we bring this data to life in a way that is accessible and impactful? So I'm talking about ways to show data in an interesting way, or maybe storytelling technologies to try to create impact with try to tell the story that you want to tell with your data. And so I'm just going to leave you with one more video. It's on National Geographic magazine actually asked us to figure out a new way or a new perspective on wildfires. The 2017 wildfire season had been pretty terrible in California, and they wanted to capture it from a different perspective.
I'm Mike Shepard, and I work at the Remote Imaging Department at National Geographic, and we're making a camera to film forest fires. And it's in a fireproof box, and it's all stainless steel and refractory ceramics. And it's got a fused quartz glass thing, and it should be fireproof. And so we're going to use this flamethrower from a hot air balloon and shoot this thing with a flamethrower to see if it's actually fireproof. And we also are reading the temperature with our sweet fire poking probe that we tested earlier with our flame.
And we've got some targets here that are in the field of view. Everybody ready?
Yep. Almost 1,000. Oh,
And it's still recording?
1,000.
Is it recording?
Yeah.
Awesome.
Sweet.
I think it works.
1,000.
So do you think, Mike, did it work?
Yeah, I think it worked. I also think that's worse than your average forest fire. You know. So.
Anyway, thank you for your attention. I just wanted to add one more thing. I'm looking forward to seeing the solutions you guys come up with. And if you have a good idea and you want money, go to www.nationalgeographic.org and click on grants and find out how you can get a technology grant to support some of the work you're doing. Thank you.